In this video, we're going to discuss how to start making the formulas for a compound from mass data. So we've done an experiment, we've measured how much of each element is present by mass, and now we want to work backwards and figure out its chemical formula. To do this, we're going to do it in two stages. The first stage is we're going to find something called the empirical formula. And then in the second stage, we're going to take that empirical formula and use that to find the actual true formula, or what's called the molecular formula. For this, you are going to need a calculator, you're going to need your notebook, something to write with, a periodic table would kind of be helpful to follow along. And once you have all of those things ready, let's go. So we should probably start off by defining what an empirical formula is. Empirical formula is just the lowest ratio that elements combine in when they make a compound. If we take glucose, which is C6H12O6, if we reduce that down to its smallest ratio, we divide everything by 6, we get the empirical formula CH2O. This, by the way, is the reason why glucose is called a carbohydrate. As we can see, we have a carbon atom and a water molecule, so we have hydrated carbon. Now, one of the things about empirical formulas, though, is that there are an infinite number of compounds that can share the same empirical formula. So this is another sugar. This is called erythrose, C4H8O4. For this, if we reduce it to its lowest ratio, we're dividing everything by 4, we wind up with our same CH2O. Right? So multiple compounds can have the same empirical formula. The only difference is what number you have to divide by to get to that formula. So what we're going to do is we're going to figure out how to use mass data, right? So we do an experiment, figure out how much of the element is in that compound, and work backwards to find the formula. The key thing to keep in mind here is that the ratios that we get are both in terms of number of atoms and number of moles, right? So for water, H2O means each molecule has 2 atoms of hydrogen and 1 atom of oxygen, but each mole of water has 2 moles of hydrogen and 1 mole of oxygen. The way that we're going to do this is we're going to create a ratio, right? So we're going to get a ratio of all the different elements in the compound, and to make our life easy, the smallest number in our ratio should probably be 1, right? So that's how we're going to go about setting it up, and the process by which we do it is going to be following a series of different rules and calculations. So first thing we want to do is we want to find the number of moles of each element that are present in that compound from its mass. If I give you grams of each element, that's great. You can just go through and calculate moles that way. If I give you percentages, then just treat the percentage as though it were grams, so like drop the percent sign, replace it with a G. The reason why is because if we assume we have 100 grams of the compound, the percentage is then the number of grams. Right, so find the number of moles of everything from that. Then our next step is we want to create the smallest number in our ratio to be 1. So the way that we do that is we divide the smallest number by itself. Dividing the smallest number by itself gives us a 1 for that. And then dividing everything else by that number gives us our ratio in terms of that smallest element. Remember, basic rule of algebra, what you do to one thing in a problem, you have to do to everything in that problem, right? So now we've got a ratio that compares all the different elements, and the smallest number is 1. If it's really, really, really close to a whole number, so if you're doing this and you get like 2.96, that's close enough to 3 to call it 3. What you don't want to be doing from this point is if you get like 2.54, 2.54 does not round to 3 because it is nowhere near 3. What we're going to do is we're going to get that out by scaling it up, right? So if it's really close to an integer, round it off, treat it as though it's experimental error. If it's not close to an integer, but it is close to a fraction, so we're talking halves, so if it's close to 0.5, thirds, close to 0.33 or 0.67, or quarters, close to 0.25 or 0.75, what we're going to do is we're going to scale everything up to make that fraction a whole number, right? So if we have 2.5, 2.5, doubling that will turn the 2.5 into a 5, so it brings it up into a whole number. And then what we did to that one, we do to everything, so we scale it up by a factor of doubling. Once you have everything as an integer, then those numbers become the subscripts in your formula. I know the process sounds kind of complex. We'll do an example of it, and you'll kind of get to see these whole sets of rules in action. So we have a compound that is 39.64% nitrogen and 60.36% oxygen by mass. First thing we're going to do, so pause right here. Tell me how many moles of each element you have present. Pick back up once you think you have an answer to that. Okay, so to find moles for nitrogen, 39.64, we're going to divide by its molar mass, which is 14.01, and that will give us 2.83 moles of nitrogen. For oxygen, we do the same thing, except we divide by 16. So 60.36 over 16 is 3.77 moles of oxygen. So here's our ratio. For every 2.83 moles of nitrogen that we have 3.77 moles of oxygen. I want to turn the smallest number here into 1, so I'm going to divide nitrogen by itself. So 2.83 over 2.83 is 1. And now because I want to keep the ratio involved, I'm going to divide oxygen by that same 2.83, and this gives me 1.33. As I was alluding to on the previous slide, single most common mistake people make once they get to this point is they go, oh, 1.33 rounds down to 1. It doesn't. 1.33 is 1 1/3. The way that we get rid of thirds is we multiply by 3. So I'm going to take this 1.33, multiply it by 3, and that gets me 4. But again, what I do to one, I have to do to the other because it has to be an even scale. So 1 times 3 equals 3. So I have 3 moles of nitrogen for every 4 moles of oxygen. That makes my final formula N3O4. So this is how empirical formula works. In the next video, what we're going to do is we're going to take these empirical formulas and figure out how to go back to their true molecular formula.